Good day, everyone. I'm Omar Mohammed, and I will be presenting for you my thesis project. The title is Measurement of Two-Phase Flow Pattern in a Linear Furnace Collector. I did this project in Industrial Solar, which is a company in Freiburg, Germany. They specialize in mainly solar thermal, CSP, especially furnace collectors. So, overview about the presentation I'm about to give today. So first I will talk about basically what is the furnace collector. Then I will go through the wire mesh sensor and the installation and the measurement procedure. Later I will give an overview about the data treatment of the measurements and calibration and programming. And finally the results and conclusion. So first, the thermal collector I have been working on is situated in Freiburg. It's a pilot plant and has a concentration factor of 25, mirror surface area of around 130 square meters, and it has double reflection, as we can see here in this image. So this is the primary reflection. It has around 70% of the irradiation. And here we can see the secondary reflection, which is a reflection mirror above the absorber tube. It has around 30% of the total reflections. And this is an example of a thermal collector. This one is installed in South Africa. With the same company installed it. The plant is running with direct steam generation technology, which is quite a new commercial technology. Okay, so conductivity wire mesh sensor. So basically there are two types of wire mesh sensor: capacitance wire mesh sensor and conductivity wire mesh sensor. The one I've been working with is the conductivity one, and basically this is a sensor that measures the two-phase flow or two-phase flow from the same fluid, or two different fluids, a flow of two different fluids. We have some example here for different applications, and basically it's composed from a set of wires, horizontal and vertical wires. They don't touch each other, so there is a gap. And within this gap, we can measure the conductivity of the fluid. So, for example, if you have water, it has higher conductivity than steam. So now we can decide that at a single mesh node, we have water, or we have liquid, or we have gas. So this is the actual sensor we have been using. From inside, we can see the wires, but we can't, of course, see the gap between the wires here. And basically, the use of the sensor is to decide which type of flow we have. So first flow is called bubbly flow. So we have mostly liquid, and then we have small amount of bubbles, and then we have stratified flow, where we have separation, total separation. Then wavy flow, a bit wavy on the upper layer of the water, and then intermittent, which is composed of mainly plugs moving on along the water, along the tube. And finally, the annular, where we have a constant layer of liquid all around the tube. We have, there is normally a different sensor for different application depending on working temperature, working pressure, and type of fluid. So installation, this is the sensor again, on site, being installed. So first thing, we installed the sensor at the end of the outlet of the absorber tube of the collector, and we have tested for leakage, fluid leakage, and so on. And then we started the measuring conditions. So basically, we had two measuring conditions: the steady state, which are the nominal working conditions of the collector, and then we tested the transient condition, which are more interesting for us. We test different conditions. So first, we change the recirculation of the mass flow rate of the water inside the absorber tube. Then we change the saturation pressure, and later we did some cloud simulation by focusing and defocusing the mirror of the collector. And finally, we have been simulating the steam demand, so we did some flashing, which is very high steam demand. And later, and after the measurements, we did some pre-measurements using the WMS software. This is okay. So I have to say this: the sensor is supplied by Helmholtz Institute in Dresden. This is the manufacturer of the sensor, and he gave to the company a software which we could convert the measurement data from analog to digital, so we could store it in the computer. So this is the okay. Yeah, this is in the process of data treatment on using the Octave program. So we can see here. So this image is 90 degrees rotated. So this is supposed to be the end of water level, and this is the circumference of the tube. So we can see here all around is higher values representing existence of water in this region, and here is steam. And this is at the edge of the matrix. We have to store the data in a square matrix, so we have to neglect all the values around. Yeah, and this is another measurement where the tube is full of water simply. Yeah. So we had to get the raw data and store them in this matrix according to the position of each mesh node we have. Yeah, this is basically a review about the programming procedure. So we have three main programs. The first is the main one. The main one set the parameters for each set of measurement data we have, this one, and then we define some directories to store the output and get the input file. And later we call the main function code, which is responsible to get some output. But first we need to set another parameter for each file, which are the frequency of a measurement. Each measurement has different frequency, different time of the measurement. And then we need to call what's called the calibration matrix. Yeah, the calibration code. And the calibration code is responsible for getting a calibration matrix where we will be able to compare the measurement matrix with the calibration matrix to be able to calibrate it later. So after getting the calibration matrix, we compare it here at the main function code, and then we could print some observable images of the flow inside the tube, the collector tube. And later we could process another set of measurement data. So this is basically the output of the project. Here we have a front section. So this is as if we have a front cross section of the tube. So this is the profile of the tube, and here this is water, and this is the interface between water and steam, and this is the scale on which we could decide if and at a single pixel you can see the pixel, very small square. Yeah, we could see also that at the interface the values are between, so they are in between, not red and not blue. So we could see that it represents a water level between the mesh nodes we have. And also very important results are the top sections and the side section. So this is only a cross section of single measurement spot or image. And here we combined a whole set of these. Here it's 1,000 of them to get a map from the view, a time map. This is time, not length of the flow moving along the sensor. So here we could see the map of the fluid. Here it's more steam, here is more water. And in the side section, as if we are looking from the side of the tube, we could see basically the level of the water inside the absorber tube. Next, more results. So here we could see different type of flow. Here we could see the stratified flow. Basically, it's total separation between liquid and gas. Then we could see a plug moving here, and after the plug it's a wavy flow. And the more interesting in some videos of the work. So this is a lower flow rate flow moving. Yeah, we could see some wavy flow, but mainly it's stratified flow. Next one. This is a higher flow rate. So we can see that it's much more wavy and plugs moving in the flow. We could see here the mass flow rate is over 0.6 kilogram per second. And again, high flow rate, different measurement. Mainly it's wavy and with plugs, but not stratified flow. And flashing, simulating high steam demand. So steam is, here you have steam moving very fast at the higher level, and the pressure also is dropping a bit, so we could see here some bubblings formed with the water boiling, since the saturation pressure is decreased. Yeah, but mainly it's turbulent and plug flow. And defocusing is, as I said before, it's simulating a cloud passing by. So basically, we only see the tube is getting filled, since there is no heat input to the collector tube, absorber tube. So it's mostly water here. And finally, refocusing again after the defocus. So now we could see that the flow is a bit turbulent, because now steam is beginning to form again. So the speed on the steam is getting higher, and so it's deriving the more turbulent flow. Okay, maybe I will clarify some things on this image. So at the top, as I said before, mainly basically, we could observe the map of the flow, how it's moving from the top, and here at the side, it's also quite interesting also, because we could see the moving plug, and here we assume that there is a lift because of the Bernoulli effect. So with the plug flow, we normally have a higher steam velocities than the water steam velocity, the liquid velocities. So that's developing a lift in this region. So it's building a plug ahead of the steam moving on. And finally, conclusion. So from the measurement, we will be able to get some interesting observations about the superheating event. So we had some superheating event. Normally we should produce saturated steam. Instead we had some overheating, and this overheating we could somehow relate it to the flow pattern inside the collector as the absorber tube. So if it's more stratified, for example, we have more overheating, since the upper part of the absorber tube is hotter, and when we have a plug flow, for example, we have less overheating, since the upper part is being cooled always by the water filling the tube. Also, mainly the main output of this is we were able to validate the extrapolated two-phase flow models, which it's basically like this map. So this map is describe the flow we should have. This is the superficial velocity of the liquid, and this is the superficial velocity of the gas surface velocity. So normally when collector is being absorber tube is being designed or a system is being designed, we have to calculate these two velocities so we could achieve the optimum flow pattern. In direct steam generation, normally it should be annular flow. I think it's this one, annular flow. So annular flow, we have a thin layer of liquid film all around the tube. So it's more or less the tube's temperature is always constant, or at least no big difference. So as similar models were being used to expect since there is no measurement in the installations, there is no way to measure this type of flow. So a similar charts were used to decide which type of flow we have. So we were able to validate these extrapolated charts with measuring our results. And yeah, this is also a result. It's not done by me, done by a colleague in the company. It was his work. So we could see here the plugs, the frequency of the plugs, and the absorber flow rate. So it depends basically on the absorber flow rate. When we have higher flow rate, we have more plugs, and it's better flow maybe. And thank you, and questions.
Thank you for your presentation. It's very interesting. Could you explain again the principle of operation of the sensor? So,
okay. Should I get the slides?
Yes.
So basically, there is a set of vertical wires,
yes,
and a set
I understood that. But
yeah. So between each wire and each vertical and horizontal wire, there is a small gap, maybe 2 millimeters or something like that.
Okay.
So through the gap, we can measure the conductivity of the fluid.
So
it's water or gas.
Yes. So that's what I.
Okay.
So the sensor is very interesting. So you have shown impressive figures, and my question is about the accuracy in transient conditions. So as you have shown, there is a large difference in the values when you have in steady conditions water or steam. So it's more or less 1 or 0. So but in transient conditions, as you have shown, how sure you are of your results? So how can you calibrate this?
Okay.
Because
for example, you mean in a single pixel, how can I make sure it's...
Yes, so in that case, it's presumable you have a fraction of steam and a fraction of water in that.
Yeah, in a single pixel.
Yes.
Okay, so normally it's my accuracy. It's not a pixel. So here it's out of accuracy. So I don't know exactly the level of the water, but I'm sure in this region that this is water. Okay, so but again with calibration. Okay, so we had to calibrate before each measurement. We had to calibrate the sensor through filling the whole tube with only liquid water. So we get more or less the nominal values for each mesh node. So these values we get different scales. So here we could see 2,500, and maybe here we could see 1,800. So this is the typical value of this node. So we can't compare one mesh node with another mesh node. So the difference will be too high. So basically, this is the calibration. We get the nominal value for each single mesh node.
Okay, but this is in steady conditions.
We measured in steady conditions the calibration.
Yes, so that you have performed measurements in transient conditions. So
Yeah, but
you rely on your calibration in steady conditions.
Yeah, because I'm only interested in the conductivity, and normally it's independent, the conductivity and independent of the condition of the measurements. So
Okay, but it's also you have a mesh in the flow, and so this may change the flow pattern as well. So because it creates turbulence, so
yeah, but it will create after the sensor, not before. So
in the sensor.
yeah, I didn't consider that because normally this is negligible, and yeah, and even in steady condition we couldn't observe any effect. So it's always the surface always smooth. We couldn't see
In
any
steady
turbulence.
conditions, it's okay. So
Okay, but yeah, I
so
didn't.
my doubts are related with
Alright. I didn't consider the effect on the the dynamics of this the wires on the measurement.
Okay. I have a question about slide 9, about the top section. I don't fully understand the previous one, please.
Okay.
So, what is on the left figures?
So
What
this,
is the x-axis and the y-axis? I didn't get it.
so the y-axis is the number of pixels.
Yeah.
So this sensor we are using is 16 by 16. So we have 16 in this direction and 16 in this direction. So this is 16 pixels, and this is number of frames or number of shots of this one.
But it is located in a single place, right? You have only one sensor.
One?
You have one sensor or several sensors?
No, only one sensor, but we start kind of extruding the flow. So instead of seeing only one image at a time, because it's a sensor we are measuring for 5 minutes, and we take a frequency of 1000 hertz.
And it is the x-axis?
The x-axis is the time. So it's this is millisecond, 1 millisecond. So this time is 1 second.
And okay, so I got it. And now the top section and the side section. I don't understand. What the top section? What it is the top section?
Okay, so I will get back a bit. So again, it's the one measurement is say for 5 minutes, and so it's 300 seconds, and for frequency of 1000 hertz. So for one measurement we have 3000 set of data like this one, 300,000 set of values of this like this one. If we put them in a 3D matrix, this is a 2D matrix. If we put them in a 3D matrix, then we have a flow. So not only a frame like this or one single shot, we have a flow. So basically, I cut the whole flow to get a top section and a side section. I trim it to get only 1000 frame instead of 300,000. But also I did an average in this direction. So I looked on from this one from the upper to lower. So I did average of all these mesh nodes, average on these.
It's in this
Yeah,
direction.
exactly.
And, okay.
Yeah, and here I'm looking in this direction.
Okay. Now a little question about the experimental setup. So it was slide 5, I think. So yeah, this one. So what is the direction of the flow? It's from left to right or right to left?
No, it's coming from here to here.
So you have a reduction. It seems that you have a reduction before your sensor.
Yes. Actually,
It did not. Is this do not imply some perturbation on your?
it
flow
should
pattern?
normally, but in this absorber tube we have a double tube. So we have a big tube which is diameter is around 80 millimeters. Yeah, it's around 80 millimeters, and we have a smaller tube inside, which is maybe 30 millimeters. Avoid tube, not the flow is not going in it, just to level up the level of the water. So the area is fixed. So the area of the sensor is the same of the difference between the two areas.
Okay, thank you.
Well, I have some questions. First, I want to tell you that I disagree with you because you have said that IDC generation is a quite new commercial technology. It's not that new and it's not commercial, from my point of view, because it is not used in commercial facilities.
My company installed one plant, and there is other companies that installed. But yeah, my company installed last year a plant in Jordan, a commercial one.
Where? When?
In Jordan, in last year.
And what is the use of this plant?
It's steam generation for industrial application.
For industrial application. So it's well, it's okay for industrial application.
Yeah,
maybe
basically.
because I was thinking in solar plant, power plant.
Electricity.
But
No.
for electricity, it's not commercial
Not
already.
the use, no.
It has been studying for a long time,
Yeah.
but not commercial.
Yeah, what I mean, yeah, it's industrial.
And I think something that I didn't understand is when you have listed the parameters, you talk about saturation pressure.
Yeah, saturation pressure. This one.
Yes. But saturation pressure, what do you mean? Because you have a, which is the circulation of the fluid. You have a pump somewhere.
Yeah, I have a pump, and normally I select the temperature I'm working on, so I can generate steam at 180 or at 150 or at 120. So if I change the temperature, I have to automatically the saturation pressure is changed. So I tested on 5 bars and on 10 bars saturation pressure. Is it the question?
But if you fix the pressure with the pump, and you are heating the flux, the water will evaporate at saturation temperature. So the pressure and temperature are linked.
Yeah, of course they are linked, but I'm not controlling with the pump the pressure. I'm controlling with the demand. So I have a steam exit valve. So when I open the steam exit valve to my application, I'm decreasing the pressure. When I close it, I'm increasing the pressure.
I see. So, and also another question is that how long it is the tube?
It's around, it's not long for this specific sensor. It's around 30 meters.
30 meters.
Yeah, it's a pilot plant. It's a pilot collector. It's very small.
Because the use of this sensor is to evaluate how is the flux at the outside.
At the exit, yeah.
At the exit. So in that way you can calculate the fraction of steam that you have at the exit. Because I suppose that in the facility that this equipment is used, you will produce about maybe 50% or 30% of steam. What do you put recirculation mass flow rate? Is recirculation mass flow rate, do you mean that not all the water is evaporated? So at the end of the tube, you remove the steam, you send the steam to the process, and you recirculate water.
Yeah, but one thing that we couldn't, we weren't able to measure the quality of the steam. We could only, with this measurement, we could only measure the volume of the steam, not the quality, because it